Hi everyone, welcome to Silicon Valley Quantum Computing Group's second session. Today's session is to talk about how to accelerate the path to quantum advantage with automated quantum error suppression. Today's we have Q-Control speaking with us, Dr. Yuval Baum, who is the head of quantum control research, and Rowen Wu, who is the staff product manager. They're going to talk to us about their product and how that is helping us. Before we start, my name is Taposh Roy. I'm the Director of Innovation at Kaiser Permanente. My work currently focuses on digital twins, machine learning, long-term modeling, image processing, and data science strategy. Prior to Kaiser Permanente, I was the head of ad products at a couple of startups, and then I also worked in consulting industry. And before that, I was the founder of a biotech company called Biointegrated Solutions. We did DNA sequences and liquid handling devices. I'm the author of the book Medical Image Processing with Deep Learning. I have graduate and postgraduate degrees in electrical and computer engineering and MBA from UC Davis. Just a note, all these thoughts and recommendations in this channel are mine and not that of Kaiser Permanente. Kaiser Permanente is not responsible for this content. Today is Feb 11th. Feb 11 is International Day for Women and Girls in Science. So the goal is to emphasize the importance of gender balance in technology, engineering, art, and math. So with that, I'll also like to introduce our volunteer, Divya Roy. Divya is a student volunteer for us. She is a middle schooler in San Ramon, California. She's an avid reader and art enthusiast, and in her own words, she loves to solve puzzles and build Legos. Her favorite programming language is Python, and she is interested in quantum computing and helping us with organizing activities here. So thank you, Divya, to be part of this group. Today's agenda is about these four things. First is Q-Control, to talk about the quantum computing and quantum error suppression. Fireside chat, I'll ask few questions, and then we'll have a open Q&A with the audience, and then some announcements. The session is gonna talk about what you're gonna get out of this session is how to get started in quantum computing, run some circuits, popular algorithms like Grover search and stuff like that, and then how to achieve quantum advantage in the NISQ area. I'd like to introduce the speakers. Our two speakers are Dr. Yuval Baum. He's the head of quantum control research. He has expertise in quantum physics and machine learning and control theory. He was part of Caltech as a research fellow in the Institute of Quantum Information and Matter. We studied different aspects of quantum dynamics and their applications in machine learning in quantum physics. Our second speaker, who's the main speaker actually, is Rowen. Rowen is a product manager focused on building emerging technology and applying it to the real world applications. Rowen has a passion to understand quantum computing. She has in the past worked on a variety of things, including IoT, AI, computer vision, and more. So we're looking forward to hear from Rowen. And with that, I'll pass on to Rowen to start with the agenda and take us ahead in this journey. Thank you, Rowen.
I'll talk about one of the greatest challenges that beholds our quantum computing industry today, and that is the error that results in hardware noise. And then I'll talk a bit about the limitations of one of the most popular schemes for solving the error in quantum computing, and this is called quantum error correction. And then I'll talk about alternative approaches that are able to supplement quantum error correction, as well as provide meaningful impact to the methods of quantum hardware use that are available today, and help to bridge the gap that lies between today and practical quantum advantage. And then finally, I'll discuss some of the results that we've shown that Yuval's dedicated research team has shown on the quantum hardware that's available today, and talk a bit about how you can apply these methodologies in order to get value out of quantum computers and run actual algorithms on quantum hardware today. So hopefully after this talk, you are super motivated to go and run some circuits if you haven't already. And you'll be quite keen to actually see the results that we are showing you here and experience them yourself. So just a quick overview on why we care about this industry. I'm sure that the fact that you're joining this talk on a Saturday morning already provides me evidence that you're interested and you believe in the potential of quantum computing. But there's a reason for companies all over various different sectors to be interested in this area as well. Companies like BCG and McKinsey have estimated the market size and opportunity in this space to be within the hundreds of billions of dollars. And we believe that the impact of quantum computing can be as revolutionary to our field and our world as harnessing electricity was during the early 19th century. So there are a ton of problems out there to solve, and the benefit is that quantum computers can actually solve problems that are currently intractable to even the highest performing supercomputers that are available classically today. The point of quantum advantage that the whole industry is pushing towards and everyone is super excited about is the point at which quantum hardware devices will be able to solve problems that are not currently tractable for today's traditional supercomputers. But the point we really care about is the point of practical quantum advantage, in which the quantum computers of today can solve problems that are of practical interest. So meaningful problems that will solve complex issues within fields of molecular discovery, of transportation and logistics routing. And one that is particularly exciting to me is improving the process of carbon capture to solve problems like global climate change, for example. So it's an incredibly exciting space, but there are still definitely limitations that prevent us from really taking full advantage of the benefits of quantum computing hardware. And the main problem that we see in the industry is noise or error. The process of noise interfering with the quantum hardware system and the physical qubits on the device, it's a process called decoherence. And decoherence basically results in the information that's being stored in the system to become randomized or not useful to us anymore. Environmental noise can result from a lot of different factors. These qubits are very fragile and very prone to sorts of noise. And this is a problem that is prevalent across a lot of different types of quantum computers. The vast majority suffers from some sort of environmental noise, whether they be trapped ion or neutral atom or transmons, quantum computers. There is this common underlying problem of decoherence. And so just to put this into a relevant frame for understanding, the classical computer, the types of transistors that we have available today, we could run them for 1 billion years at 1 billion operations per second. And that would be the duration of time that we would likely be able to run them before encountering any type of error. Generally, across the quantum tech industry, and this is on average across the various different types of hardware I've mentioned, that time span decreases to 1/1000th of a second. So that's the amount of time that a quantum computer or a single qubit on a quantum computer can go before experiencing some form of noise. And so, as you can probably surmise, it is extremely detrimental if there are errors being introduced on the order of seconds to the system. And what this results in is we'll see that if you try to run an algorithm, even a fairly simple algorithm, such as in this case, we're showcasing the results of Grover's search, a small circuit of just 5 qubits. And Grover's search is basically a quantum algorithm that is akin to finding a needle in a haystack. It's a form of unstructured search that basically helps to detect, in this case, a single bit string across a totally unsorted stack of additional bit strings. And even in this case of this relatively small circuit, a relatively small number of gates, we see that when executing the circuit on the default platform, just the bare metal hardware, and we'll talk a lot about this default today, we see that we get pretty much unintelligible results. It's pretty much, at this point, just random noise. And you can see that the ideal answer is to get a single bit string that is decipherable from the rest. But in the case of actually running this algorithm on the quantum hardware, the results are completely obfuscated amongst all of this noise that has impacted the system. And this problem actually increases in intensity as system sizes scale. So as we get to larger quantum volumes and larger circuit widths, we see an increased impact of error that makes pretty much running any circuit unintelligible across the noise that happens within the system. And so this is extremely challenging of a problem because in order to get towards the point of practical quantum advantage and running algorithms that are actually useful to industries and solving industry level problems, we'll have to increase the number of qubits and we'll have to increase circuit depths as well as width in order to be able to solve these challenges. And if the performance of quantum computers is only declining as the system size increases, that poses a huge problem in terms of actually deriving any meaningful value out of these types of systems. So let's talk about the positives. The optimistic outlook is that quantum error correction is a highly probable and very well-researched way of providing some sort of redundancy within quantum information systems. So the theory behind quantum error correction, to simplify it drastically, is really just based on a common concept that is already used in classical fault-tolerant computing. And this concept is called triple modular redundancy, aka TMR. So a simple example of TMR is just to have three systems that are performing a process, and you use simple majority voting by looking at the states of the three systems, saying, well, if two systems are the same, then we can assume that that is most likely the correct state. And so if one of the systems fails, there are two others that can mask the error and correct for the fault. So the application in quantum error correction is basically to take the state of one logical qubit and to spread it out across a series of physical qubits. And this can help to build resilience against local failures. And it is a theory in which we can build arbitrarily large quantum computers by helping to use these systems of entangled qubits to help to capture the current state of a single logical qubit. So quantum error correction, it has a lot of attention within the industry right now. It is quite a popular field of study. And all of these studies actually have just come out since 2020, meaning that there have been many meaningful improvements to the field, resulting in larger code blocks, better ways of encoding states, better ways of repeating measurements. And it's really a field that is super promising towards the industry right now. But there are still oftentimes some issues that prevent quantum error correction from being something that is practical and scalable. And that tends to be the reason why a lot of people still see us as being quite a ways away from completely fault-tolerant quantum computing. One of the major reasons for the lack of scalable quantum error correction today is just sheerly the amount of overhead that is required in order to make quantum error correction useful in practice. So performing a single syndrome measurement, which is basically just this measurement that in which you look at the states of the entangled qubits in order to try and derive some sort of meaning about what the state of the logical qubit is. In order to perform one of these single syndrome measurements, depending on the topology of the machine and the gates that are being operated in the encoding process, it can take hundreds to thousands of operations in order to just derive one single measurement. And so in the addition of these hundreds to thousands of operations, then we multiply the number of potential error possibilities that can arise. And so we need an extremely low baseline error threshold that comes from the encoding process as well as the hardware error gate limits. And in order to achieve any sort of meaningful quantum error correction, we'd have to have this extremely low baseline error threshold to make this process work. In addition to the amount of overhead involved that introduces a duplicity of errors, we also require quite a high amount of resources in order to implement quantum error correction. So if we're to assume a fairly low error threshold of around 10%, and this would involve having a nearly perfect decoder, and using a fairly well-researched way of encoding topological quantum error correcting code called the toric code. And in order to achieve a logical failure rate of about 10 to the negative 15th, this is a very low failure rate, but it is also what is commonly seen across research as being, the state at which things are become useful. The resources required to achieve this super low error threshold and error rate, they increase exponentially as we decrease in the actual physical error rate. So in order to encode a single logical qubit at this rate of error and given these various assumptions, we would actually require hundreds of thousands of qubits in order to represent a single qubit, a single logical qubit. And this just becomes completely infeasible and impractical if we're to have just, a small number of logical qubits on the order of 10, then we would require millions of physical qubits. And most of the quantum processors out there and available today, they're on the order of maybe tens or maybe hundreds of qubits. So as you can see, it's quite a ways away in order to achieve practical quantum error correction at scale. So there's several ways in order to get us closer to the point of practical quantum error correction. There, in theory, can be advancements in the encoding with higher error thresholds. We can come out with better hardware with better incoherent error bounds and better gate error rates. And then there could be broadly more hardware homogeneity in which we can assume that in these quantum error correction schemes, we're looking at the worst case versus the best case error rates of a system. So if we can improve the broad hardware error rates overall, then that improves the thresholds needed to make these statistics possible. And then if we're able to improve error statistics, we can improve the temporal and spatial correlations that help to actually make all of these mathematics that are involved actually work out. So there are quite a number of different factors that we can improve upon in order to make quantum error correction something that is feasible. But one of the specific areas that we're looking towards that we can actually actuate upon today is the by taking quantum error correction and looking at it as a form of feedback control. So at its simplest form, quantum error correction is very similar to a typical type of quantum control theory. So if we can look at the quantum error correction feedback loop that is the core basis of the theory, we can look at it in the context of a block diagram, which is just a common way of representing classical control theory, in which we have a single variable that we're looking to influence. In this case, we're representing it as the plant, but basically you can think about it in these terms as the encoded quantum bit. And it's being acted upon by a controller. And this controller is what is actually influencing the state of the plant. In the cases of quantum computers, it's oftentimes using pulses or gates. And then we really care mostly about the top part of this block diagram. And we can utilize something that's called open control theory to act on this top part of the diagram. And open loop control is just a type of control that is super simple and low cost, and it doesn't take into account any feedback into the system in order to actually make actuated results on the object in question called the plant. So you can think about it in terms of a simple sprinkler system. A sprinkler system that turns on every single morning at 8 a.m. It doesn't take into account the moisture level of the soil. It doesn't take into account what season it is or whether or not it rained the previous night before. It will just come on no matter what at 8 a.m. And that is a form of open loop control. And so quantum control is really a field that stems from this concept of applying classical control techniques to the open loop part of the system. And it is concerned with how the classical world interacts with quantum devices. The field of quantum control largely owes its existence to decades of research that have already taken place in fields such as NMR and electron paramagnetic resonance. And in those fields, the hardware is quite limited due to the ability to characterize molecules spectroscopically. And the problems that we see in those fields are quite analogous to what we see in the field of quantum computing, in that there's difficulty in measuring and actually being able to characterize the state of the system. And so these theories have been developed since, the early 1950s and have been continually applied and produced to specifically target the problems that occur in quantum hardware. And so a lot of different methods within the field of quantum control have been developed to suppress errors and improve the ability to execute algorithms error-free and decrease the physical qubit error rates, and thus improve resource efficiency. And so the field of error suppression is a more broad field that is applying these sorts of techniques within quantum control and broadly within the field of control physics in order to improve the error thresholds that occur on these quantum hardware machines. So here I've just shown some of the various different techniques using quantum control theory, some of which involves utilizing the information that we get about devices, about their pulses, topology, and the actual gates themselves in order to improve the schema of how the actual circuit works and how it will be implemented on the machine in order to best execute the circuit with the lowest error rates possible. I won't get too much into these. They get quite into the actual theories and specific research methodologies in quantum control that Dr. Yuval's team has spent a lot of time researching and applying. But these methodologies, if you want to learn more about them, please feel free to ask us during the Q&A section. For those of you who are maybe more advanced or even experts within these fields of error mitigation or error suppression, we love to talk about it, and we love to also showcase our results. We have lots of technical manuscripts and research published, and we can refer to that as well if you're interested in reading up. So in practice, we see quite significant results from applying quantum control to the hardware systems that are generally available today. In fact, looking at the same Grover search algorithm that was previously shown in the early slides in this deck, we see that we're able to take the completely incoherent results that we came across on the default system, and we're able to make them into something useful. So as you can see, when applying these error suppression techniques, we are able to take a completely randomized distribution and turn it into a distribution that actually reflects the correct result and then the intended result of what we're looking for in this algorithm. And these results actually perform up to 1,000 times better, meaning you're 1,000 times more likely to achieve the correct output, as opposed to if you were to just run your algorithm using the hardware that's available. And we actually see this effect becoming more pronounced as system sizes increase. And so, as I was mentioning, it's necessary for practical quantum advantage to get into larger system sizes, to get into higher quantum volume. And in order to do so, we actually need to provide and to implement certain error suppression techniques in order to actually get a meaningful output. And so we see that, at the smaller quantum volume, the benefits of applying error suppression techniques, just because they're not as necessary, the benefits result in around 100 times improvements. But as the coherence of the machines drastically decreases across larger quantum computer sizes, as the number of qubits increase, then we see that the benefits that you can get from quantum error suppression actually become closer to what we cited as 1,000 times X improvement. And so looking back at how to apply these error suppression methods, I mentioned quite a few advanced techniques on our slide on quantum control. And you may be thinking that, well, it sounds like it will require quite an in-depth research, as well as learning a lot of different methodologies that require perhaps advanced knowledge of physics or control theory. And even though there are SDKs today that provide naive implementations of these sorts of quantum control or error suppression methods, it can be quite a complicated process to actually apply these methodologies. And it requires oftentimes many steps of configuring to figure out what the exact setup and implementation should be. It also oftentimes requires sampling methods, which means that you run several different circuits on a machine in order to just figure out how to appropriately account for the error that arises within just that specific hardware system. And all of this can just lead to a lot of additional burden and overhead that prevents you from getting to the stage where you can actually run a valuable circuit. And a lot of this is, a lot of it's boilerplate code. And as people who, are software engineers or familiar with common programming paradigms, we want to reduce the amount of boilerplate code that is actually not benefiting our end solution at all. And so what we've come out with in our as our company, Q-Control, due to the advanced research and the methodologies that we've developed, we've come out with an automated error suppression pipeline. And it's packaged up into a single package called FireOpal. FireOpal is the epitome of what we're calling this performance-enhancing quantum infrastructure software. And it applies all of the best methodologies within the field of quantum control and error suppression. It is able to distill all of this down into something that doesn't require any sort of knowledge of the underlying systems or the specific backend that you're interested in running quantum algorithms on. And it actually allows you to simply focus on the algorithm design aspect of getting results from quantum computers. So all you have to do is take your circuit or your algorithm in question, you submit it to FireOpal, and FireOpal will execute on behalf on a number of different supported hardware backends, as well as utilizing cloud-based services that provide access to a broader range of hardware backends. And in return, you receive the best possible outcome given the results applied and optimized using the Q-Control methodologies and techniques. And so that's where you're likely to see the right answer as a result, as opposed to these completely randomized distributions that oftentimes you would see if executing on just a bare metal machine. And under the hood, what we're doing is we're applying several of these error suppression techniques that I previously alluded to. across the actual compilation, as well as throughout the execution process, where we're aware of the actual hardware limitations that exist on the specific machines that you'll be running on. We help to mitigate for those, and we help to optimize your circuit in lieu of those limitations. And then we perform some post-processing as well in order to actually help to mitigate the errors that arose during the process. And all of that in turn means that you're getting the best possible results back when you execute using FireOpal. We see in practice that this continuously delivers the best results that help to improve hardware to near its performance limitations. So there are certain boundaries that as software we cannot modify and we cannot change, but these are known as kind of the T1 or T2 limits of the machine. And these are just ways of quantitatively measuring quantum decoherence and characterizing it in terms of the actual amount of time that qubits are actually usable on the machine. So these hardware limits, we're not getting anywhere near them today using the default configuration of the machine. As you can see, as the number of qubits on the machine increases, the difference between what the theory supposes that the hardware should be able to perform and execute differs drastically from what is actually possible. And the likelihood of getting success on these theoretical limits is actually very, very low when you get to a larger number of qubits. FireOpal is able to get you much closer to the T1, T2 thresholds of the actual hardware itself, allowing you to take the utmost advantage of what the quantum hardware has to provide, and actually to execute longer and deeper circuits. And even in comparison with the expert configuration, which is using the most advanced and aggressive compilation schemes, as well as the best possible error mitigation techniques available in research and in open literature today, we see that this degradation in performance is still quite clear, and it can be drastically improved with FireOpal. And in practice, what this allows you to do is, with FireOpal, you can run circuits that are much longer and deeper. And so that actually allows you to run much more interesting problems and much more interesting algorithms, and actually to achieve results on them with using actual quantum computers. And this even applies to various different algorithm types. There's a lot of interest in the industry today in hybrid quantum classical algorithms. So these are algorithms in which we're utilizing the advantages of classical computing for optimization routines. And we're also using the benefits of quantum computing in reducing the overall number of operations involved. And this hybrid quantum classical technique is used in a lot of optimization problems in some of those industries that we mentioned that are very interested in quantum computing, such as transportation and finance. And we're able to utilize algorithms like the quantum approximation optimization algorithm, also known as QAOA, to get results that are not possible on just the quantum computer alone or just the classical computer alone. FireOpal is able to optimize the quantum aspect of this quantum classical routine. And we can see this visual indication of just how much the performance is improving by showcasing the simulated cost landscape, which is basically just a visualization of what it means to get the actual lowest possible point within this optimization problem. And we see on the default hardware, it's the imagery is completely different from what we see in the simulated landscape. With FireOpal, the optimization landscape is much, much closer to what you see in a simulated environment. And what that results in ultimately is much faster convergence. So each time you're performing QAOA, you go through this cycle of running on the classical computer, running on the quantum computer, and this can ultimately result in even achieving the wrong answer after, hundreds of repetitions. But with Fire Opal, we see this number of repetitions reduced drastically to, a factor of 28 times faster. And we see that the results actually converge upon the correct local minimum or local maximum. So all of this put together, we get back to the original theory that we were considering to get us to the point of practical quantum advantage, the quantum error correction feedback loop. So if we think about quantum error correction as just one of these many algorithms that we have shown and demonstrated impact upon, we can show that Fire Opal also produces significant results when applied to an algorithm of quantum error correction. So what we do is we measure the actual error suppression techniques when executing a quantum error correction schema, and we see that the syndrome extraction process is much improved, such that actually measuring the error and getting the correctly identifying the right error, that entire process is drastically improved using Fire Opal to run the scheme. And it's based on the same methodologies of optimizing gates, of eliminating crosstalk, of improving the overall execution of the hardware. And so, as you can see, the means of getting to practical quantum error correction are drastically improved and accelerated by the usage of these sorts of error suppression techniques. These practices, these theories are highly complementary to one another. And so, in summary, you should be able to take these sorts of techniques that are available today and actually derive meaningful results from the quantum hardware that is available today, even given how limited it is due to the inevitable error and noise that is introduced in the system. Hardware is, essentially the key to getting us closer to the point of practical quantum advantage. However, we can help to bridge these gaps using these techniques within the field of quantum control. And you can leverage this in an entirely automated pipeline using the package Fire Opal, which we've shown the proven results that have been benchmarked. And so you can go ahead and get started today. You can sign up for Fire Opal. It's completely free. Our goal in providing access to Fire Opal is really to showcase to people that are currently running on simulated machines that you don't have to stick with just simulations at this point. Even given the NISQ devices that are available today, it's possible to run algorithms and get real results. And actually, it's necessary in order to formulate quantum algorithms that are going to be able to scale to larger system sizes when they're available. You have to develop them and test them on real quantum computing hardware. And so with that, I will conclude my portion of the presentation, and I'll hand it back to you, Taposh, for our fireside chat as well as the open Q&A section.
Sounds good. So I'll start with a few questions, and then anybody from Q Control can answer. I mean, the first question is very obvious. I mean, first of all, impressive talk. Thank you for that. And impressive work done by the Q Control team. So the question is, once the quantum error control is in place, will that make the error suppression obsolete? What do you guys think?
Yeah, so I've talked already a lot. I'll let Yuval get his share of talking in the morning.
Yeah, so I think like Rowen said, it's not independent, right? Quantum error corrections, these are just quantum circuits. We must have quantum error corrections in order to make quantum computing useful. But no error correction will ever work without a classical error suppression. It's not and, it's not or, it's and. We must have both, and in some sense, we are already now showing that we can make quantum error corrections a bit better. Even in days where the hardware will be extremely good, and in general, you will be able maybe to use quantum error correction. The ability to push the errors even an order or 2 orders of magnitude down can lower dramatically the overhead that you need. I think, as Rowen showed, these days, maybe each qubit need to be represented by thousands of qubits. So if you have a circuit of 1,000 logical qubits, and each one need to be represented by 1,000 qubits, you need systems of million qubits. But with classical error suppression, if you can lower that to only 10 qubits, then maybe you don't need millions of qubits, you just need thousands of qubits.
That is very impressive, and within the NISQ area, and I recently put forward a paper for medical image processing using quantum computing, basically just using IBM Qiskit. And I think I should definitely use Opal there and see how it works. I'll send you the paper we have put together. It's in the IEEE CHI for healthcare. So next question is, which quantum hardware is most likely to succeed? And there are variety, as you know. I mean, the breadth of it is large. I mean, what do you guys think from your perspective?
So we try not to be opinionated about that. You know, we are not in the business of gambling. So Q-Control, I cannot talk about specific collaborations, but we work with parts of the sector across all hardware providers, superconducting, photonic, trapped ions, atoms. It's very hard to know which hardware platform will win. It may even be that, you know, in the future, different hardwares will dominate different parts of the industry. It may be that we'll just have some competing platforms that will just coexist, and some people will choose to use that, and some people will choose to use that. Like, you know, like today with classical computers, there are definitely competitors out there, and they can coexist. So it's very hard to know. And we are trying to be as agnostic as possible and not to take sides there.
Can you tell me a few things about, can your methods that you're currently using for error suppression, will that scale up to hundreds and thousands of qubits in the future? Will that do that?
Yes, so that's the most important question, right? In order to reach quantum advantage, we need to be able to scale. I mean, it's very nice to run something on a 20 qubit device, but eventually, in order to see real benefits, we'll need to go to hundreds and even thousands and tens of thousands eventually. Right. So we definitely put a lot of effort and attention to that. All the methods that we develop, we try to make them as scalable as possible. The ideal scenario is that they scale as we call O of 1, which means that the effort to do it for 20 qubits is completely identical to the effort of performing that for thousands of qubits. For some of our methods, O of 1 is not possible, but we definitely try to keep the scaling linear or sublinear, which is something that is still very appealing and much better than any exponential scaling. There are some challenges that are not just Q-Control challenges, are industry challenges. It comes to compilations and other steps in this pipeline. So probably if tomorrow you'll give me a 1 million qubit system that is operating, I think that some of the tools that we have will struggle. But I'm quite positive that by the time that we'll have a 1 million qubit device, our methods will be completely compatible with that.
Yeah, perfect. One last question, and then I'll open up to audience for questions. So today we are in a NISQ area, and a lot of people are developing applications. If they want to engage with Q-Control, what's the best way to do that? Is it just download the package and use it, reach out to you? What is the best way to make that? And let me add one more twist to the question is, will Q-Control just provide the optimized circuit, the quantum circuit, and they need to talk to the IBM or whatever they're using, the bracket or whatever they're using? How does tactically things work?
Yeah, that's a great question. On the surface level to the user, basically all they need to really do is sign up for an account, download the package, and then we can basically interface with any sort of hardware backend necessary. They will still need to configure and sign up for an account with the hardware provider in question, meaning that, you know, if you're looking to run on IBM backends, you sign up for an IBM account. We're looking to alleviate this process by working with cloud providers like Amazon Bracket. and Azure in order to leverage this intermediary system to make it easier to run across various different backends. But for the user, it's super simple. They only have to interface with one sort of software, being Opal, and then in order to get signed up and started, and even started on the path towards being able to develop quantum circuits, we actually offer a range of different products. As Q-CTRL, we have also an educational platform called Black Opal. We have kind of this theme across our products of being Opal themed. It comes from our Australian background as a company. But Black Opal is a great educational tool to even get started, even learning about the basics of quantum mechanics, all the way up to programming your first quantum circuit and learning all about the specific algorithms that were mentioned in this talk and more. So all of this is self-serve, and you're able to just go ahead and get signed up and started today.
Okay, I'll sign up today then. Thank you. Okay,
Thanks, Taposh.
I'm gonna open up for audience questions. Anybody in the audience, they want to raise their hands or speak up if you have a question?
Sure. Thank you, panel, for the impressive talk. This was really, I'm still new to the quantum world. But my question is about the journey of quantum computing itself. Do we ever think that quantum computing will deliver on the dream of personal computing? As I understand, it's very expensive. Or do we feel that it will mostly be, provided by big service providers like IBM, Amazon, as a quantum computing as a service?
I can start, and then maybe you can. Of course, it's a hard question, and the fact that we are all ears, so I guess we do believe that there's a lot of potential there. I don't think that we'll have quantum laptops, right? So it's not a personal computer. We'll definitely have these centralized computers, which is not that different if we think about the direction that classical computers go, that you just access via the cloud pretty much unlimited classical resources to solve your huge problems. So we are definitely very optimistic that we'll reach that point, that in the near future, where we can solve problems that classical computers struggle with. It doesn't mean that in necessarily a year or two we'll have a completely fault-tolerant, completely millions of qubits, but we don't even need to go there in order to declare success, right? We just need to show that we can solve a relevant problem of interest, not some engineered problem that we can actually solve, that classical computers cannot solve, and it makes economical sense, right? If solving a problem is something that you need to spend much more than you'll gain, then it doesn't make any sense. And I can't give you a date if it will be in 2 years or in 10 years, but I think that it's not that far as some people think.
Yep, totally. And to answer part of your question about, can smaller companies make an impact? Is it just going to be the big giants out there that are, gobbling up the quantum computing industry? I think that we definitely are seeing a lot of impact from all sorts of directions. And so what's actually really exciting about the space right now is that it's so fresh that so many different companies have a stake in the game. And really depending on the research that comes out in the next couple of years, as well as the advancements within the field, there's really the possibility that anyone can win at this moment. And there won't just be one single winner. As you've all said, a lot of different technologies can coexist, and some might be used in certain applications and some might be used in others. And so we see a lot of companies right now that, are small in size and number of employees, but that are having enormous impacts on the industry and overall the dynamics of, the quantum computing field. So it's quite, an open field right now, greenfield approach, as some would call it.
Sure, thank you so much.
Maybe I can add to that. If we learn something from the classical computer revolution that we had, is the importance of software, right? If hardware was the most important thing, Intel was probably the most important company in the world, because they make the actual chips that sit in our computer. But without software, these things are not accessible to everyone and are not the most important things. And when it comes to software, size is not the most important thing.
Sure, thank you. I do have one more question, but I'll just type it on the chat in order to be
Yeah,
courteous to other panel
yeah.
members. Thank
No,
you.
appreciate that. Is like we have time for one more question. Anybody else other than Preeti you'd like to ask?
Yeah, I
I
think
do
that
have a question.
Sure.
It's regarding Fire Opal. So it's almost too good to be true because it's highly automated. It reduces the errors and whatnot. I believe you're using multiple methods like deterministic and AI and whatnot. Is there, let's say, is there risk that you might introduce actually error or bias your method? Or to say it differently, how can the end user be sure to trust the results in the automation? Aside from bugs, of course, that can always happen.
So of course we are very careful not to do these things. That's part of our research. In some sense, the trust is by running these things on small enough computers, so you can use strong classical computers in order to benchmark and to see that whenever you use FireOpal, you are always closer to the ideal result. At some point, when we'll go to big enough, then it's only trust, right? Because you'll have nothing to compare. You just have to believe that what you get is indeed the case, which, I mean, in some sense, that's the stage that we are with classical computers. When you run a very complicated program, you may wonder if there is a bug in your code, but you never doubt that given that your code was executed correctly, maybe your computer just decided that 3 by 3 is 7, right? It's not something that you think about. You just assume that you'll always get the right result. And I think that eventually we will get there. And as people will use right now, as Rowen said, just go and use it on the small devices, not because you can do a meaningful calculation on a 7-qubit device, but it will show you that when you use our tools, you always get results that are better than the default and closer to reality and not biased, hopefully.
Yeah, it's a question that we get a lot in terms of it seems too good to be true, like what's happening on the background that is allowing these sorts of impeccable results. And I think an important consideration to take into account when thinking about like the integrity of the algorithm or the circuit itself is that we don't do anything to change the underlying circuit. And so while we might replace certain gates with more efficient gates, the actual algorithm of like what is happening and what is the desired and intended result of the encoded routine, the program, is not being changed in its integrity or its fidelity at all in any sense.
Okay. Thank you. We are almost at time, and I want to give the last 1 minute to my friend Dimitri, and I'm going to share my screen and show his profile. Give me 1 second. I'm going to share the right screen. Okay. Dimitri, the floor is yours.
Hello. So I am a software scientist. I have a lifelong love of physics and mathematics. And I only recently started getting into quantum computing because it's a natural field that combines all my interests. So I started a meetup for people who are interested to learn quantum computing in depth. And I am going to put this on the chat here. So this is for non-experts who want to learn the material. We are mainly studying from this book, Quantum Computation and Quantum Information. So if you are interested, you can join the meetup. Experts are also welcome. They can help us out. And if you are interested in physics specifically, I am also participating in this meetup, co-hosting it, called Physics with Friends, which I put there. And if you are more interested in the mathematics behind quantum mechanics and quantum computation, there is also this group called Quantum Formalism, where they deliver lectures on various mathematical subjects like group theory, Lie groups, measure theory, functional analysis, etc. So yeah, that's what I had to say.
Thank
Thank
you.
you.
Thank you. Thank you, Dimity. With that, I think we'll end today's session. Really appreciate everybody joining early morning. I know it's 9 a.m. for people in the West Coast, so thank you. And we'll talk to everybody again later. I think the next session is on quantum cryptography, and I'll let you know more about it soon. So thank you, everyone. And special thanks to the Q Control team. Really appreciate you being here. Thank you. Bye.
Thanks
Thank
so much
you.
for having us,
Bye-bye.
Taposh.
Bye.
Bye.
Everyone.
Bye.